Hey there guys, welcome to your part 1 video notes for chapter 1.4, Thinking Scientifically. Now, we're first going to start with some exponents review. Really important since IB is international. There's a lot of different words we use to represent exponents throughout the world. Exponent, which you may have been used to, power, but index is something else. So you may see something said raised to the power of 2, or with an exponent of 2, or with an index of 2. Base is just used interchangeably to represent the exponent or what is being multiplied by itself. Whereas, the index or exponent or power is used to represent how many times we're multiplying that base by itself. So some common examples we know are, for example, 5 to the third power just means 5 times 5 times 5. Now you can also use variables with exponents, so x squared is just x times x. But you can also use variable or algebraic expressions such as x plus y squared. Well, that means my base is x plus y. So I have to do x plus y times x plus y, or multiply the base by itself twice. We'll also go into a little bit into negative exponents. I'll skip this final example so we can go to laws of exponents. This is not going to be on your formula sheet given to you, so you have to know generally some basic laws of exponents, so I would copy this down. Generally what you need to know is that anytime you see a variable by itself or a number by itself, it has an implied exponent of 1. But same thing as we never really write 1x, we don't really write x to the first power. It's implied. Whereas anything to the 0 power is 1. So for example, 700 to the 0 power is 1. 7 billion to the 0 power is 1. 8 trillion to the 0 power is 1. Anything to the 0 power is 1. Now, exponents are a very special case. Exponents, or negative exponents, is generally something we don't like in mathematics. Anytime we have a negative exponent, we want to turn it positive. Now, the way to turn negative exponents positive is to kind of flip around what sign it is. So it generally helps, if it's not already written as a fraction, is to turn whatever base you have with the exponent into a fraction. We know we can turn any whole number or whole variable into a fraction by writing it over 1. Now the negative exponent tells me I'm not happy with my place. So the way to make it happy or positive is to go to the opposite place. So if it's in the numerator place, we're going to put it to the denominator's place. And now we have 1 over x to the positive first power, and like we said, we don't really write it, so 1 over x. Here's another example. You write it as a fraction, which we just write it over 1. Since it's in the numerator, we're not going to write it in the denominator's place. Now, it just doesn't have to be 1. You can have any number for a negative exponent. We still do the same thing. So here we have x to the negative third power. We are not happy. My exponent's negative. To make it happy, to make it positive, I have to flip to the other side. Now it's happy. Now it's positive 3. And you'll see more examples of this. Some other laws of exponents that are really important to know. Whenever you're multiplying exponents with the same base as each other, you add them. So for example, x squared times x to the third power. You add 3 plus 2 to get 5, x to the fifth power. Conversely, anytime you're dividing exponents with the same base, you subtract. So x to the sixth power divided x squared, well, 6 minus 2 is 4, x to the fourth power. This is very different. Notice here, when you're raising an exponent to an exponent, this is called the power law of exponents, you multiply. This right here, right here is very different than this. Usually, you're raising exponent to an exponent because you'll see parentheses. So for example, x squared raised to the third power, you multiply it, 3 times 2 is 6. So make sure you know the difference between when you're multiplying exponents and when you're raising an exponent to an exponent. Also, the distributive law still applies to exponents. So if we have the fraction x over y and we're raising it to the nth power, that n distributes to the numerator as well as the denominator. So in this case, x over y squared, the squared will go to both of them. So you'll get x squared over y squared. So let's actually put these laws into practice. So we want to simplify these numerical expressions. So the first one, we have 2 over 2 to the third. And we know anytime we have a variable or number by itself, it has an implied exponent of 1. We know when we divide exponents with the same base, we're really subtracting. So keep the base, subtract the exponents. 1 minus 3 is negative 2. But like I said, we don't like keeping things negative. We want to make our exponents happy. So we're going to write it over 1. And we know it's not happy in the numerator side, so it wants to flip sides. Now, that's in the denominator side, Now it's happy. 1 over 2 squared. Here we're going to apply different laws of exponents, so we're going to take it step by step. First, we have to simplify the numerator. In this case, we're multiplying bases with we're multiplying exponents with the same base. So in this case, we know we're going to add 3 plus 5 over 4 squared. 3 plus 5 is 8. So we have 4 to the 8th power over 4 squared. We know when we divide exponents with the same base, we subtract. 8 minus 2 is 6. You get 4 to the 6th power. Here, this one's different than here. This time we're not multiplying two bases that have exponents. In this case, we're raising an exponent to an exponent. So this is where you multiply the exponents. So 2 times 3 is 6. So our numerator simplifies to 4 to the 6th power. And we haven't done anything to the denominator. We know that when we're dividing bases that have exponents that are the same base, we subtract exponents. 6 minus 3 is 3. So we're left with 4 to the 3rd power. Now finally, really, really important, we can use these laws of exponents if they have the same base. 2, 2, 4, 4, 4, here's a 4, here's a 4. Notice these are not the same base. So you can't tell me it's 5 and then 4 minus 4. You can't really simplify this any further besides putting it into your calculator and getting a very large number. So be aware of that. They have to have the same base for you to do that. Now, like we said, bases can be variable values, so we can still apply the same rules. So this is power to a power law. We're raising exponent to an exponent, so we just multiply. That's x to the 6th power. This is our distributive law that tells us we have to distribute it to the numerator and the denominator. So we get 1 to the 1st power, then x squared raised to the 4th power because it's had an exponent. This means we're raising a power to a power, so we're multiplying these two exponents on the bottom. And we end up with 1 over 8, or x to the 8th power, because 4 times 2 is 8. And we don't really write 1 to the 4th power, because that's just 1 times 1 times 1 times 1, which is just 1. This one, we're raising a power to a power again, so we're multiplying, so we end up with x to the negative 3rd power. But it's not happy as it is, so since it's in the numerator, it's going to get moved to the denominator to be happy. And now we have a positive happy exponent. Here's another case of where we have to apply multiple rules at once. So first we have to clean up the top. So same base, and we have to add these exponents. So since it's not power to power, it's just basic multiplication. So 3 plus negative 1, or just 3 minus 1. 3 plus negative 1 and 3 minus 1 is the same thing, over x to the 5th power. Gives us x squared over x to the 5th power. We subtract. 2 minus 5 is negative 3. Oh no, it's not happy. So this answer also ends up being 1 over x to the 3rd power, because we turned our negative exponent positive. Now we're going to get into scientific notation, so just the general of it. Really important, scientific notation is also known as standard form. Now scientific notation is generally written in the form of a times 10 to the nth power, where a is a number between 1 and 10. If you have a positive exponent, then you have a number greater than 1. And if you have a negative exponent, then your original number is less than 1. Now looking deeper into it, scientific notation is just a convenient way for us to represent very large or very small numbers. For example, Avogadro's constant is written typically as 6.022 times 10 to the 23rd. It would take 24 digits to write it fully if not for scientific notation. So you can really see how that's a time saver. Now into some of the basic math behind scientific notation. Generally what we're doing is breaking down numbers into 10, or using our 10 multiplication rule that lets us know that we can move decimal places by multiplying or dividing by 10. So for example, we write the number 700 as 7 times 10 to the 2nd power scientific notation. What we're really doing is saying, hey, I know 700 is really 7 times 100, and I know 100 is just 10 squared. So still the same number, we're just writing it kind of in the shorter end way. Now the general rules for converting numbers into scientific notation is that if you're moving the decimal place to the left, your exponent goes up. If you're moving the decimal place to the right, it goes down. So for each decimal place, or for each digit you're moving left, The exponent goes up that digit. For each digit you're moving right, the exponent goes down that digit. Now, to know where to stop moving your decimal place, you move the decimal place until there's one digit to the left of the decimal point. So for example, here we have 1, 2, 3, 4, 5, 6 digits to the left of my decimal point. That's too many. We just want one. So I want my decimal place to end up here, where there's only one number to the left of my decimal place. So to get there, I need to move 1, 2, 3, 4, 5 digits to the left. So this is positive 5, 1.56 times 10 to the 5th power. Typically what you do for scientific notation, you'll write the numbers that are non-zero, and you'll drop the zero numbers. Now sometimes you have really small numbers that are decimal values. Still the same idea. You want to put the decimal place so that you have one digit to the left of the decimal place that's between 1 and 10. And then to get here, I had to move it 1, 2, 3, 4, 5, 6 decimal places to the right. So since I moved 6 decimal places to the right, my exponent went down 6 times. I have 5.3 times 10 to the negative 6. So that's the general rules, but we can do some more examples. So here's some more general examples. If we have a positive exponent, such as 598,000, I want my decimal place here. To get there, I need to move 5 decimal places to the left, so it's positive 5. If I want to convert the number 481 into scientific notation, I want my decimal place here, where there's one number to the left of the decimal place, which means I have to move 2 decimal places to the left, a positive 2. And if I want to represent the number 123 right here, I'm going to want my decimal place right here, and I have to move 7 decimal places to the left. Now, generally, I know that for positive exponents, I'm representing numbers larger than 1. So that's how I know to check whether I'm using the correct positive or negative exponent. Whereas for negative exponents, I'm converting numbers like 0.031, numbers less than 1. Now, in this case, I'm going to want my exponent to be here. So I'm going to move it 2 paces to the right. For the next one, I want to represent this number in scientific notation. My decimal is going to go here. To move my decimal places there, I need to move 7 places to the right. And then finally, for this example, to write this number in scientific notation, I want my decimal to go here. To do that, I need to move my decimal place 4 places to the right. Now, something also important to know, your calculator, you may have seen it depending on what kind of math problems you've done, tells you things in scientific notation, but it uses a very special calculator notation, which is a to the e to the nth power. This EE button in your calculator is how you're going to use scientific notation. Don't just write 10 or times, like a regular times, 10 to the, second power. Use this for scientific notation. But be aware that your calculator is going to give you your answer in scientific notation. However, during the exam, do not use calculator notation as your answer. Answers must be clearly written using scientific notation. So your answer should be 3 times 10 to the 5th power, not 3 e to the 5th power, which is what your calculator will show. The e just represents the times 10. But once again, don't just use the calculator times 10. So here's our final practice, going between forms. So in this case, I need to move 9 places to the right. So let's see, 1, 2, 3, 4. That's already 4 places. 5, 6, 7, 8, 9. That's 9 places. Here, it tells me what it is. I know this stands for times 10. So my base is 3.65. The e is times 10. And my exponent is -4. Here, I want to write it in calculator notation. GDC is just graphic display calculator. So this is going to be 7.8 times 10. 7.8 e to the 6th power. And then finally, this is 3 times 10 to the 2nd power, or just 300. Make sure you're able to do this on your own. It will be on your skills check. So we'll finish this up in your Part 2 notes. Don't forget to complete your Delta Math homework, as well as be prepared for your skills check. Your first test is August 31st. If you have any questions, feel free to email me or message me a reminder. Otherwise, have a nice day.